Hello everyone, my name is Mikkel Hegnhoj and I'm here to introduce you to SpinCube. SpinCube is an open source project which streamlines developing, deploying and operating WebAssembly workloads in Kubernetes. It is collaboration between Microsoft, Liquid Reply, SUSE and Fermyon. Fermyon is the company I represent and I'm head of product at Fermyon. SpinCube is part of the Spin framework together with Spin. Both of these are open source projects which are in the process of being donated to Cloud Native Computing Foundation, where they've both been accepted as sandbox projects. Spin is the development tool that you can use to build WebAssembly microservices and web application using a serverless application model. And with SpinCube, you are able to run Spin applications really efficiently inside of Kubernetes because they're powered by WebAssembly. So SpinCube has already seen adoption where, for instance, Zeiss has been using SpinCube with Microsoft's Azure Kubernetes service to create really fast, scalable applications that can run a high density while still making it more easy to operate these applications. So they've actually done proof of concepts and have been running applications where they're able to bring down the compute cost with 60% without any doing trade-offs in terms of their performance. So let's maybe unpack how all of this works and what can lead to these amazing results. So to give you an overview of how these things fit together, I mentioned that Spin is the open source project that you would use for developing applications. Now, when you have a Spin application created using Spin, you can run these inside Kubernetes using SpinCube as a free open source project. Fermyon also provides some hosted options using Fermyon Cloud that's fully managed. And we also have a set of enterprise features around SpinCube called Platform for Kubernetes. Part of that being that you can achieve even higher density than what we have with Kubernetes. But we're not going to get into that today. We'll mainly focus on SpinCube as an open source project. So SpinCube consists of 4 different pieces. There is an operator to help translate the application model or application framework that Spin is into a Kubernetes language. So basically, Spin applications ends up running as pods and through deployments and having services, all these native Kubernetes resources that we all know. But we have the Spin operator sitting as a wrapper around all of this that enables you to easily translate between the concepts you use in a Spin application and the concepts inside of SpinCube. It's actually optional to use the Spin operator, and you can just create your deployments yourself, referencing Spin applications as OCI images. But as we start to unpack all of this, and you'll see some details in a live demo, you'll get a better understanding of how these things fit together. The runtime that enables us to run Spin applications really efficiently inside of Kubernetes is part of a containerd shim called containerd shim Spin. So basically, at the containerd, the container runtime layer, we install a shim on your node so we're able to tell containerd that in the case that we want to run a Spin application, a WebAssembly application, we're actually not going to use your regular container runtime. We're going to use a different shim for running the WebAssembly, which means that you won't see your regular C groups and all of that on your nodes as you run the WebAssembly. And part of this is how we can get to higher density in some of those scenarios inside of Kubernetes. There's also the runtime class manager. Really, the runtime class manager is here to help ease up the configuration set of containerd. So in particular, if you have Kubernetes clusters where you rely on auto-scaling and adding extra nodes into your cluster, having a configured runtime class manager enables you to set up your nodes dynamically to be able to run the Spin applications. And the final piece of all of this is the SpinCube plugin. So part of the Spin developer tool, there is a CLI, and basically the SpinCube plugin makes it really easy to transition from local development, scaffolding YAML, to pushing your Spin applications into OCI registries. And we'll get to see that again once we get into the demo. Let's try this out and let's take a look at how this all works. And I'll start by basically creating a small application. So let's transition over here. Okay, let me just give you a few references as we go along so you have those. Spin framework has its own GitHub organization. We're still in the process of moving everything over from where these things were previously as part of all this contribution into CNCF. But you can see you have Spin, the development tool, as one repository, and then you have some of these components that I talked about, like the Spin operator, the containerd shim Spin, runtime class manager, and then there are various SDKs for Spin that are also part of this. So Spin framework is a good place to go on GitHub. SpinCube has its own documentation, which is SpinCube.dev or website. So basically SpinCube, the dev, contains all the documentation you would need. There are a few blog posts in here as well for certain scenarios. And we'll get back to some of these as we walk through building an application with SpinCube. And when you need to build an application with SpinCube, you need to go to developerfamily.com for now, which is where the Spin applications are. The Spin documentation is to be found. And the reason why I'm saying for now is because, again, part of the transitioning and contribution into CNCF, these things may move around a little bit, but definitely stay on Spin Framework GitHub and we'll be able to guide you there. You'll also be able to find both Spin and SpinCube channels inside of the CNCF Slack, where you can reach out and interact with maintainers and other people that are part of the community. Okay, so with all of that in place, let's actually try and get this built-in application that we can run inside of a Kubernetes cluster. So the few things that I have prepared here is I already have a cluster running. This is a local K3D cluster that I've created. If you want to run this in Microsoft AKS, there is a marketplace offering where you can easily configure SpinCube. And on the SpinCube documentation, there are a lot of guides in terms of how to get these running on Kubernetes clusters and microcades, Azure, Rancher Desktop, and just in general how you can install SpinCube with Helm. And if we really quickly want to run through this, we rely on Cert Manager in order for SpinCube to run. And then we install the runtime class, previously known as KWasm operator. That's the one, the runtime class manager, enables us to install container DSM. And then we can go and get some CRDs in. There are a few custom resources we need for the Spin operator, the Spin runtime classes, and the Spin app executor. And finally, there's a Helm chart to basically install the Spin operator. And yes, that should be it. Now we got to the point where we upgrade and uninstall, but let's not do that now. We want to try this out first. So hopefully you get this idea that even though there are a few things you need to set up, all of these are regular things you would expect from adding this kind of frameworks and functionality into a Kubernetes cluster. So I've already done all of that. And if I can find my cluster again, you can see beyond Cert Manager, what I have is I have the Spin operator installed down here, and I also have the Jaeger installed, so maybe we can look at some traces as we go along. Okay, so that's all that I have inside of my cluster for now. So before we get into how this all works inside of Kubernetes, let's just quickly create a Spin application. The way that you create a Spin application is basically there's a Spin new command. You use the template to create applications. In this case, I'm using a template that is set up to take HTTP requests and is written in TypeScript. Let's just call this HTTPS. We're going to name the application Conf42. And let's go into the directory and let's take a look at what we have. A few things got created for us. Main thing is the spin.toml file, which describes our application. I think the main thing to take a note of here is you have this concept of HTTP paths or triggers. So there is a wildcard route, meaning all HTTP requests coming to this application is being handled by this one WebAssembly component down here that is named Conf42. And Conf42 is basically a WASM file, so a WebAssembly binary file. I'm not going to spend time going more into the details of the whole JavaScript to WebAssembly and how these other things works. You can find a wealth of information on Fermion's on Fermion's YouTube channel, where we have a lot of videos that sort of help you understand even the WebAssembly part and all of that. So if you want to dive more into the development pieces and how this all works, highly recommend go and check those out. All that is just interesting to know here is that Spin has a concept of this application manifest, which is what I'm showing you right now. The other thing that we have is then obviously our JavaScript. And just for the sake of making this a bit easier to grok, let's do this. I'm just going to run an npm install so that I get all the npm package that I need. In this case, I need this router. To give you an idea of how these Spin applications, like we talk about them as serverless, but basically what this means is that we have an event listener, in this case, an HTTP listener that you implement here. And in the case of using this IDI router, what basically we do is you can set up various functions that reply to various HTTP requests based on the routes being called. So basically in the case that we call a root, we're just going to say hello universe. Actually change that to Conf42. And let's make the capitalization of that's correct. So if we'll send an HTTP request to the root, we'll just say hello conf, and we will say /hello/something. We will reply with hello to whatever we passed in on that path. All of this is just stuff that happens in this IDI router, which is a JavaScript library that you can use, but I hope it gives you a sense that Spin applications are meant to, they're basically triggered by HTTP event. They're going to do their thing, they're going to shut down again, and we will see how we can use that in terms of scaling things and so on a little bit later. Okay, so this is basically our application. Let's try this out by using a spin build command. So now what is happening is we're going to take the JavaScript and through a set of build tools, we will have a WebAssembly WASM file coming out on the other end, which gives us a lot of the benefits of portability. They're small, they're secure, because they run inside of sandboxes, and they start up really fast. And we can see that if we do spin up, which actually loads our spin application. And now we can call the spin application locally. And you can see hello Conf42. And if we do hello there, you can see hello there. Okay, so that's pretty straightforward. We actually have a small spin application now powered by WebAssembly. We can reply to a few different paths. Okay, we want now to get this into Kubernetes. Usually what we would do with containers, and the workflow is similar, because really one of the core objectives in terms of how we wanted to design SpinCube was to just make sure that WebAssembly became, you could say, a first-class citizen inside of Kubernetes. So when you want to, which means that when we need to distribute this application, for instance, we rely on OCI to do that. So if you have an OCI registry already today, that will be compatible with moving the Spin applications into Kubernetes clusters. And you'll see that once we get a little bit further down in terms of how the CIDs and all of this work. Okay, so now we want to use the SpinCube plugin. So I just want to make sure again that I built the latest version of my Spin application. I'm just doing that because I've sometimes forgotten how to do forgotten that I wanted. Sometimes I forgot to do that. Okay, then we're going to use a command called spin registry push. So basically now I can push the Spin application into a container registry. And I am going to use, let's do this. I'm going to use TTL-SH. This is an ephemeral, publicly available container registry, or OCI registry, which is really nice when you want to do demos like this. So what is happening now is Spin is going to take my WebAssembly application, the manifest that were created, and any configuration that I may have, package those as 3 individual layers into an OCI image, and push it to this registry. What's really important here is that's the only thing we're pushing. We're not creating file system, whole layers of file systems. Dependencies are not brought in because they're already compiled into the WebAssembly binary. So if we go ahead and actually inspect the image that we have inside of our registry, we should be able to see that the only thing in here, I'm just gonna go up so you can see, there's a bunch of annotations. Oh, I even got my name in there, which is nice. And you can see there's a small config JSON, which is 209 bytes. Then we have our WebAssembly, which in this case is 12 megabyte. We can strip and we can compress this even further, but it's only a 12 megabyte binary that we're moving in, and then the actual Spin application manifest as well, which is 534 bytes. That was the TOML file that I showed you. That's really all that there is there. There isn't a bunch of layers with dependencies and other things that I need to bring us along. This is all that we're going to move around. And this is one of these things where WebAssembly is super interesting in terms of having smaller images and having fixed binaries that we actually move. Okay, now the next thing I'm going to do is I'm going to use commands to easily create my deployment. So in this case, I'm going to say SpinCube scaffold. So basically scaffold the YAML that I need. Use the container image path that I just created, which I pushed to and put this in an app YAML file. So if we look at this file, you can see we have a Kubernetes YAML where we are using the SpinCube dev API. So this is part of the custom resource that are being created as we deployed. We created the custom resource before, but this is part of the whole SpinCube project, where we actually have a Spin app resource in here. This very much looks like how you would create a container or deployment. More actually, in terms of we have replicas in here. And I think I mentioned earlier on, you can consider this Spin app resource to be a way to try and easily translate what we saw in the spin.toml file, because, and we'll do that a little bit later by adding variables in here. There's an easy transition between these two, but they all end up just being deployments and containers. Deployments and pods, sorry, not containers. Okay, so now that I have this, let's move over and give this app YAML file to a Kubernetes cluster. And what we'll see is, first of all, we can go and take a look at the spin app, where we now have this Conf42 spin app created. So this is the spin app resource I'm looking for. We want to have 2, and we can see 2 of those already now. We can see the description in here, basically what we expected. What you can also see is there's actually a deployment created. So again, we're creating a real deployment. We could have chosen to really just create the deployment if we wanted to, but that sort of takes the spin operator out of the picture. And there are various things that we use the spin operator for. For instance, here I'm able to have a cluster-wide OTel endpoint that I create, which means that I now have a Jaeger instance in here. So all my spin apps will automatically adopt that OTel configuration. So there are some benefits you can get from all of these. So yes, highly recommend using the operator and using the spin app resource for doing this. We also have a service that's set up for us. So what we can try and do in here is we can go ahead and port forward to our service. Let's do 8080 because that's the way, that's what I normally do. And if I don't, something will go wrong. So we've now created this port forward, which means we can go back here and we can then curl to 8080. And you can see hello conf, and we can do hello there. And I just need to get my spelling. There you go. And now we have hello there and hello here, so on and so forth. We can see this all works as it works locally. So that's it. We've actually taken a spin application that we created from scratch, used TypeScript, and saw we can run this locally easily, and piled this into WebAssembly, created an OCI image that we pushed, created the spin app resource inside Kubernetes, and there it is, and there it is running. Let me go back and just, I want to do, let me check. Oh, this one. We can see there are actually 2 pods behind this, right? You can see there are the 2 pods being created in here, and this is also where we can go ahead and find our logs. There's an open telemetry error. Let's just not think about that, but you can actually see that we did hit the spin application in one of these pods. I think one thing that I wanted to show you around the Jaeger instance is that I have Jaeger set up in my cluster as well. And if I go ahead and just look at something that Spin is doing for me, we can see that not that long ago, we were actually hitting the Spin application, and you can see we have the whole OTel configuration being in here. We were getting there was an HTTP GET request for the root, and what happened is that SpinCube then executed this WASM component called Conf42. So to give you an idea again of how much work that's actually been put in to make it really easy to give a lot of the stuff that you say, these are just like table stakes today, you want to have OTel, you want to have all of these things, and it's really easy to get this set up and running with SpinCube and your Spin application. Okay, moving ahead from that, actually, let's just do a quick recap of what happened here. So we did spin new to create a new application, spin build, created a WebAssembly, registry pushed this into OCI. You can use any OCI image you want. If you have a private registry, which I hope you have, I think it's spin registry login, and then you would basically be able to log into that before you push. Again, all of these can easily be run in a CI setup as well. There are actually GitHub actions that exist out there to do all of these things with Spin. And then we did Kube Scaffold as a nice little tool to scaffold our YAML and applied that to our cluster. What happened when we applied it to the cluster? The resource was being put into the API server as a Spin app custom resource. The operator picked that one up, created deployments and services, and now we have that Spin app running in a pod. But in the pod, the runtime class manager makes sure that container dshim is there, so we are actually executing using the container dshim spin and not using the regular container runtime. And yes, that's it. I was just thinking about how we can actually, I don't think there's an easy way for me to show that, but that is how that works. I think what we can see actually, if we looked at the actual pod, we should be able to see in here that, let me check. You can see the runtime class we use is wasm spin v2, and basically that runtime class is what informs containerd that we want to use the spin runtime. Wasm is wrapped inside of Spin, but we only use the Spin v2 version of the runtime to actually run this. It's not being run in a normal container. Okay, let me go back and showcase another scenario we have. So we have this application now, and let's just try and see how this, again, how having an application like this, using something as simple as providing a variable to our application, how all of that works with a regular Kubernetes workflow. What I would do in a Spin application to begin with is that I need to add a variable into my Spin file. So basically what I'm going to do in here is I'm going to say that I have a variable for my Spin application called myVar, and there's a default value to that, which is Conf42. Then the other thing I can do inside of Spin is I can say as part of my component down here, so the hello, it's not called hello Conf42, it's just Conf42. Part of this component variables, there's a variable that I want to pass onto my component, and the variable that, or the string that I want to use for this comes from the myVar that is created up here. So basically what this enables is inside of Spin, I can now go to my file, and I can do two things. I can import, if I get the import correct, a way to get variables using the Spin SDK. And then the other thing that I've done in here is I've just prepared a small piece of code. Let me do this, and I think I will need to do an npm install to get the package in. And let me just check what's going on. Get rid of that one. Okay, so what I did in here in my code is I imported the variables from the Spin SDK, and now I'm setting out another path in the router saying if someone calls me on /var, I will basically reply with my var is, and then I'm going to get my variables from the my component var, which is the one that we just added into the toml file. So now that we have this created here, let's go back and do a Spin build. We're going to rebuild our application, and then we can do a spin up again. So basically run this application, and if we, let's do 3000 and then var, you can see we get the default value, which was Conf42. I can also set this var by using spin underscore variable underscore my underscore var. Basically, if I set that environment variable, when I run spin up, I've now provided the variable, and you can see my var is now something else. Okay, that was the local story to get an idea of how these things work together. Now, what I want to do is I want to push this into my cluster. So I'm just going to make sure I have the latest build. Once I have that, we can do a registry push. Let's do version 2. So we're going to push the new compiled WebAssembly, the new spin.toml that still has that default value in it, Conf42. But what we will do is we'll just bypass that for now, and then we'll actually provide a configuration through the app YAML that we have. So we don't need to create this again. We can basically just go in here, and we can add variables as easy as, as this. So let's say we have variables, and we have a variable called myvar, and just want to make sure we get indent right. Let's say the value is Kubernetes because we're in Kubernetes action. Let's say the value is SpinCube. That's more nice in what we're doing here. You need to remember to update the version. Okay, so basically we now updated the Spin application, the Spin app resource definition to pull in the new version of the image, and we provide variables. So if we do apply this, we can go back and we can see that we have new containers creating, and we should soon be able to see that the previous versions being taken down. And so at least I think we have, this was the new version. Let's check. Yeah, we have one, which is version 2 of our image, and we should have 2. Oh, that was refreshing. Yes, we now have 2 of the new version running. So we got those quickly deployed. Let's go and check if our forward is still set up. It's not. Let's do this. Forward to the service once again. And we can go over here, and we can now curl an 8080, and we would expect to see myvar is SpinCube. Okay, so that was one scenario where basically, again, just wanted to show how variables can be added and other things. You can obviously have the variable being pulled from a secret. If we take a quick look at the API documentation for the Spin app, you can actually, instead of doing that, let's just look at an example because I think that's more interesting. It's easier to see. Assigning variables. In this scenario, basically, This is part of the spin configuration for the example that's gone through here, what we did in the spin.toml file. But basically what you can see down here is how you can use both config maps and secrets to provide this. And then this would be what the spin app would look like. So you have, this is what I did, an inline variable, but we could also have the variable be from a config map reference or from a secret reference. And all of this would look very familiar to how you would do this normally in deployments when working with containers, regular containers inside of a Kubernetes cluster. Okay, let's actually do check on this one, because we did see, yeah, you can see this was the trace from where we're actually using the get. So you can see spin is fully instrumented, and then we can see we're actually calling another method inside of the spin SDK to actually get the variable, which was pretty quick in terms of how that variable was gotten. And if we want to dive even further into this, because why not? What we can see is that the way that all of this sort of ends up being set up is that the actual pod, let me just check. We're looking at the pod right now. The actual pod has the, let's see if we did the YAML. The actual pod has that spin variable myvar set up as an environment variable, which is the same way that I got this environment, this variable injected when I ran things locally. So again, gives you an idea of how the operator works and what value it adds inside of the whole stack here. Okay, let's try something a little bit more fancy, because part of the benefits we get from using WebAssembly rather than containers is how quickly they can scale, because the small size, how quickly we can pull them in, but also how fast they will actually start up. So a good scenario would be something like combining this with KEDA as a scaler inside of Kubernetes. So what I will be doing now is let me just check, because I think, yeah, we already have KEDA running in our cluster. I think what we can, so what I will do is, based on the tutorial that you're able to find over here in the SpinCube side, which is called Scaling Spin Apps with Kubernetes Event-Driven Autoscaling, so basically using KEDA. This is an example that walks you through how basically there is an application that creates a lot of CPU load, but obviously using KEDA, you can scale based on CPU load, you can scale based on observing queues or other things. I think even object stores. There's a whole bunch of stuff that KEDA can do. But again, because everything with SpinCube is so integrated into how Kubernetes works, most of the Kubernetes ecosystem and most of those projects that are out there will actually just work out of the box with SpinCube. So what I've done is I've added KEDA into my cluster right now, and all of that is something you can do inside of this article. So what I'm going to do now is I'm just going to apply this KEDA scaled object. Basically, this is KEDA's way of saying, well, actually, this is the application. Sorry, I'm going to add the application to begin with, and then I'm going to create a KEDA scaled object, which basically is the one that is monitoring the spin app, changing it between 1 and 20 replicas based on CPU and based on 50% utilization. So that's threshold for when we add another replica, when we take down a replica. So the few things that we need to do here to make this work is to go to our terminal. And the first thing we're going to do is we're going to apply the sample application. And the next thing I am going to do is I am going to apply the scaled object. So if we quickly go over here, we can see we now have a KEDA spin app. We actually had minimum 1. I believe we could change this to 0. Try that. We have auto scaling set to true. Red bishop is 1. I think we would have to, whoops, we got stuck. Let's get out of here. This one says minimum 1. Anyways, let's not do this now. Maybe we can play around with it a little bit later. I just got myself all excited about whether we could actually do that or not. Anyways, let's go back and monitor the spin app. We have that here. I think if I do control R, that will be refreshing. So we can see we have one of the KEDA spin apps running already, translated into one pod. So what I'm going to go do now is I'm just going to create some requests to the application. Before I can do that, I need to set up a port forward. So let's set up a port forward to the service. Let's do 8081 and back and take a look at the spin app. Here we have it. And then we can go over here. And now we have load. And we should fairly quickly start seeing that more pods needs to be spin up of the KEDA application. Let's go and take a look at The parts over here, we can see CPUs at 429. Oh, there you go. Okay, now things are starting to happen. We got a bunch more of the KEDA apps. And if we come back, we can see we're now at 4. And we should gradually see this changing. Let's just go back and stop some of the HTTP requests. We got 9 responses back. This is not a case of performing. This is just a case of showing how these things work. And you can see that this all works. We got extra parts. We got more of these spin apps running inside of our Kubernetes cluster. And I don't quite recall whether the app will actually ever stop again or will just keep increasing. But at one point, we should see that the number would cool down, and we'll then have fewer of the spin application instances of the web application. That was a few examples of how you can get started, looking at using variables and other things, and also how this works really well with other projects like OpenTelemetry stacks. Jaeger in this case is what we saw, and even Kubernetes event-driven autoscaler. We might actually see, yeah, this is the CPU load. So we can see a bunch of those coming in as well. Don't know whether those would actually ever complete or not. Few resources to go for: SpinCube.dev, and you can get to learn a lot about SpinCube. Developerfermion.com is a good place to get some spin documentation, and Spin Framework on GitHub is the place that you go and take a look for this. Okay, so hopefully along the way, you've got the idea that SpinCube like just easily flows into your regular way of working with Kubernetes and your workflows you have around CI/CD and all the other things you can do around Kubernetes. There's obviously the question of why do we need Spin WebAssembly applications in Kubernetes? And I think there are four very particular things that you want to consider, and why I think this is super relevant, and why I think this is a way that we can bring even more value and so on into Kubernetes. First of all, as I showed you, the Spin applications are really small. So comparing to a lot of containers where you potentially bring in a lot of dependencies and all of these, you have a single binary that needs to bring in. You potentially have some configuration, and maybe you have some data that you bring as well. But a hello world Spin application that's not written in JavaScript, but written in Rust, can be as small as a few hundred kilobytes. That's the OCI artifact that we need to juggle around. So this gives us a lot of great opportunities in terms of if we need to run these things and we want to use Kubernetes as a workload manager or a scheduler, even in environments that have little compute capacity and power, this is something that can potentially make that work with Kubernetes, so you don't have to rely on containers. Another part of this is that the WebAssembly components start in less than a millisecond. Actually, the execution model, we haven't really talked about it, but the execution model in the world of Spin and WebAssembly is that the component, and maybe we want to go back and look at this file just to give you a idea of what I mean. Let's look at this. So you can see that there is this, the way that a Spin application is defined in here, we have this idea of, or this concept of a component, right? So we have an HTTP trigger that maps to a component. The component is the WebAssembly file. So I can easily create applications where I have multiple of these components, and so each WebAssembly file represents a different path on the route or a different set of functionality inside this application. Whenever a request hits our application, what happens inside of the runtime is that the WebAssembly binary is loaded, the request is handed over in memory from the host to the guest in this case being your application. It's handing the request, and then we're unloading the WebAssembly module again, which means that if you had 4 or 5 different WebAssembly modules in here, for each request, only the modules that needs, or the components that needs to be loaded are the ones that are going to be loaded, and that we will use for this. Which also means that as soon as the work is done, the WebAssembly is unloaded, so it's only the host runtime that takes up memory on your Kubernetes node. And this is where the higher density that we can get from running WebAssembly actually comes from, is that there's very low minimum memory consumption that is taking place. And there are even ways, and this is where some of the enterprise add-ons that we build at Fermion come into place, where we can get fully rid of the memory footprint. So basically truly scale to 0 as part of how these run. So that's another very important thing and a lot of value that I think Spin WebAssembly applications will bring into Kubernetes through SpinCube. Then there's the third thing, which is that sandbox. So this is the security part of this. So a WebAssembly component is a sandbox and is denied access to resources on the system, which means that it does not have access to file system. It does not have access to memory outside of its own memory linear memory that's provided by the host when it's loaded. Also, you have to explicitly grant access to HTTP endpoints or other network endpoints that you want to access. So there's a way inside the spin.toml file where you provide access to particular API endpoints, whether that's a SQL database, a Postgres database, Redis endpoint, Valkey endpoint, an HTTP endpoint. You have to do that explicitly. So this is a nice operational runtime decision that you can make of which endpoints are available for the actual application. And finally, you have the portability across processing architectures and operating systems, which means you can swap out the underlying node processing architecture without having to produce separate pipelines and deploy artifacts, meaning that the same OCI image could run across x64 and ARM64 devices. So if you're able to use some of those in your either cloud environment or other environments where you run Kubernetes, you don't need to deal with multi-arc images and all these multiple build pipelines. The same WebAssembly binary will actually, in one compilation, would run across all of these processes and architectures. So again, it dramatically simplifies. I guess a scenario would be if you have a workload where you can utilize things like spot instances, or what they're called in the cloud. You can really subscribe to spot instances provided as ARM instances, x64 instances. There's a lot of opportunities there to also have some cost savings associated. So with that being said, I hope this gave you a good idea of what SpinCube is, how it works, its relationship to Spin, and some of the benefits you will get from using this. So highly recommend go and check out spincube.dev. Spin documentation is on firmware.com/spin for now. And thank you so much for listening. Have a great day.